So today we'll get into projects. So I have a couple slides just to sort of get the ideas flowing, and then it's kind of up to you to define what your project will be, what most interests you, what you want to work on, and we were just talking about what we're going to do for the tape outs, but I think figure out what project excites you the most, and then we'll kind of strategize on how large the project is, how well it fits into the area that we have, and how many of these we think we can tape out. Yeah, so we'll talk about defining your projects, and then it's your time to design and debug them, and then hopefully by the end of the course you can go through the submission process. Like I said, I won't be here on Friday. But hopefully at the end of Friday you can go through the submission process. Even after you submit, you can make changes. So if you want to continue working on your projects after that, that's fine. So just some general project ideas. Each of these bullets I have an individual slide on, I believe. So the calculator circuit that we made makes a really good tiny tape out project. It's kind of the right size, the right scope. There are things that you could do with your calculator. You can enhance it. I guess I'll wait for the slide on that. I should probably show also, we have these various PMOD devices that are external devices that you can plug into these boards. So let me just kind of pull out the toys and talk about some of them. So for the calculator in particular, this keypad is quite useful, right? So you could make a calculator that takes keypad input. The keypads, I figured after I ran my first course, I figured, okay, let me take an hour in the evening and whip up a controller for the keypad so students can use it in the course. It took me like 2 days to put the controller together. The documentation was just wrong in every way possible. The signaling integrity has issues. So it was just unbelievable to me how poorly documented such a common sort of commodity item could be. Maybe that's a lesson for some of the other documentation and a cautionary tale. I'm not sure, but I did create a TL Verilog controller for the keypad that you can use as a component and connect up to your design. Let's see. And these are things that I can leave here. So this one also very useful for the calculator, 4 buttons. So even with your existing calculator, you can play around with these buttons as input, right? So this would be your calculator has 2 buttons for the operation and an equals button. So one of these buttons becomes your equals, and you push the other buttons to set up the operation. So that's useful for the calculator as well as other things. I have a few of those. Actually, these are all buttons. There must be another bag here somewhere. This one. There are a couple additional LED lights and 7-segment displays. Looks like these are all 7 segments. So you have the 1 segment on your board. This you can plug in sort of as an alternate to the one that's there on the board to give you 2 segments. Basically the way that works, of course you have 8 pins, so how do you display 16 segments? The decimal point on this is not used. It's used to select which of the digits you're lighting up, and basically you set up your circuit to just keep bouncing between the 2 faster than your eye can detect, and your eye doesn't know the difference, doesn't see the flashing. It just looks like both digits are lit up. So those are good to play with too. You could extend your calculator, for example, so you can show the full byte. I think this one's an ambient light sensor, if I remember right. This one's a little speaker. I haven't played around with these, so you can explore and try to build an appropriate controller. This one's a light sensor, so maybe this one wasn't. What is this? PIR, I'm not sure what that stands for. Passive infrared? Okay, so another sensor. A UART controller that, again, I haven't experimented with. But that might be good if you want to be able to communicate with your silicon. LED lights. So I think this gives you just a light for every output pin, 8 lights. So I think that's everything. So those can be fun to play around with. Keep those in mind. So you could also enhance your CPU. Keep in mind, I think the CPU that we designed occupies 2 tiles, if I remember right. So, maybe play around with your CPU to reduce it from a 32-bit machine to an 8-bit machine and see if you can fit it on a tile. You can create something completely from scratch. Create a device controller for one of the PMOD devices. You might look around to try to find an existing Verilog or TL Verilog design that you can try to fit on tiny tape out. You could, even if you don't specifically want to do a tape out, you could kind of explore this space by doing a study or optimizing logic, things like that, to focus more on the quality of results of the build flow. So ideas around enhancing your calculator, I think we kind of mentioned this along the way. So the two-digit PMOD to show the 2-digit value. So we implemented a single value memory. You could enhance that to implement multiple memory locations. So you could set up your operand to specify which memory address you want, and then hook up the memory operation to store at that memory address, and same for recall, to recall a particular memory address. You could look at the multiply and divide operations, right? Multiply and divide for our calculator was just star and slash. It was really easy in code, but that small amount of code implies a large amount of logic. There are more efficient ways to implement, iterative multiplication, division over multiple cycles. You could look at the arithmetic there. I know there's a lot of course content at this university around arithmetic circuits. Enhancing your CPU. I think most of these ideas would probably grow your CPU, not shrink it. So that's a consideration, but you could look at, enhancing it for a specific application domain, right? Maybe extending the CPU core with specific instructions for that domain. So, for example, adding instructions that natively support parity calculation, or byte-wise operations, or adding a simple branch predictor, perhaps, to look at performance improvement. Right now, the CPU, all it's hooked up to do with the outside world is show passed or failed, right? So you could think of some way to hook it up to the output pins, maybe even control an external device, something like that, to do something more interesting. Certainly you can hook it up to display values on the 7-segment display that's on the board. You could sort of use the CPU as a calculator, and compare the CPU implementation of the calculator to the native implementation of the calculator. You could do something completely from scratch, so just a bunch of ideas to get the juices flowing. This top one I like, and nobody's latched onto it yet. Mm, looks like the URL is no longer valid or something. Huh, okay, well, site can't be reached. Um, so this is a little electronic game that I had when I was growing up that we would play for hours in the car driving to camp and drive my parents crazy. So it's basically it's a path, it's a button on either side. So two players, and the lights light up. So the lights go sort of one light at a time, kind of go back and forth. So you're, I don't know, basically batting a ball back and forth. And the closer it is to your button, when you push your button, the faster it shoots back. So you're kind of waiting till the last second as much as possible to shoot it back really fast and try to score against your opponent. So it's a game called Zap. Just, I feel like it maps really nicely to the resources that we have, right? You can easily light up the LEDs. One of the examples that the Tiny Tape Out put together as a walkway example is a padlock. So you use the input as a combination for the lock. You configure the lock to a particular combination, and then only when the inputs are driving that combination can you get a value out of it. So you can program it to a particular combination, you can store data in it, and you can retrieve data out of it with the right permission. So that makes a nice, simple example that maps well to the hardware. Alarm clock, something like that is good. A die roller, right? Die roller is actually really simple. You just run a counter, and when you push the button, it stops, and you show the value. As long as the counter is fast enough, it's random for all intents and purposes, right? You could make an up-down counter, right? These are all sort of simple circuits that make good, good first forays into using TL Verilog and doing digital logic. Elevator controller, right? So mimic the controls of the elevator. Keep track of what floor the elevator is going to. Stoplight controller. These are both very typical intro to digital logic examples that are used in classrooms. A digit display sequencer. So what do you do if you only have one digit to display, but you want to display a 4-digit number? Well, you could sequence the digits and display them one at a time. So maybe you can create a little controller for doing that sort of thing. You could, kind of similar to what I was suggesting, creating the memory for the calculator, you could create a design that's more specifically that memory, right? So be able to store values in, load values out, maybe do a FIFO, first in, first out kind of queue structure, last in, first out queue structure, a little memory that you can configure in either orientation, first in or last in, or random access. You could make some sort of a sorting logic to sort numbers. If you prefer the drag and drop style, you can do a walkway project instead of a maker chip project. Any of these ideas, you could also explore a CPU implementation of the functionality, and if you want, compare that with a custom implementation of the functionality. You can make controllers for one of these devices, like the keypad or a VGA display, for example. Video display. So if you want to create a device controller, some examples. So UART, SPI, I2C, I2S, these are all examples of simple bit streaming protocols for communication. So you could look at implementing those protocols. The the keypad controller, as I mentioned, 7-segment display controller, audio, rotation. I don't think I have the rotation um, device, but I have the speaker, I believe. Things that you could potentially port to Tiny Tape Out. You could look at Warp 5. Again, that's going to take more than one tile. There are a couple maker chip examples that you could look at. There's a sorting network example. There's a maze solver example. So for the maze solver, I wouldn't directly use what's there, but doing a maze game, I mean, doing games in general is a fun thing to do. So you could certainly do a maze game. You could imagine the 7-segment display being the walls of a maze and use that to show at least the walls that are immediately around you. And, you know, sort of be semi-blind going through a maze. There's this project called Serve that's the world's smallest RISC-V CPU. I would imagine you could fit that onto a tile. Probably somebody's done it already, I'm not sure. But that's a good design to do in the context of RISC-V that, you know, you might be able to fit on a tile. It's an interesting design because it's bit serial. So instead of having an ALU that, for example, can in one cycle add two 32-bit numbers, they have arithmetic logic that calculates 1 bit at a time. So your 2 operands stream in bit by bit, 1 bit each cycle, and each cycle 1 bit of the result comes out. And they use that. Actually, Olaf is the creator of that. Olaf Kindred, I've got his name wrong. But he's a very active open source contributor, very active in the RISC-V community. And this is his design that won one of the RISC-V contests. So I would guess that it would. I don't specifically know that. You might have to do some things to pare it down, like remove CSR registers or something like that. I'm not sure. Yeah, so for the tiny tape out flow, I mean, we sent the calculator through the flow. The file was already configured for you that has the options such as how many tiles do you want to use. That was already set up for 1 tile. But you configure those options, you run synthesis, and if it doesn't fit in the area you give it, it will fail. If it doesn't meet the timing that you ask for, it'll fail. So you play around with those parameters and you know, repeat the flow until you get the results that you're looking for. If you want to do more of a case study as opposed to a submission, you could explore the ASIC and/or FPGA implementations of your CPUs, explore the pipeline version, explore the non-pipeline version, compare area, power, performance, things like that. You can look at, again, the arithmetic operations, and, you know, kind of study. I'm guessing many of you have probably been exposed already to arithmetic circuits in your courses. You might take some of those things that you've been exposed to in your courses and try implementing them and do some studies. Some of the things that were done in prior iterations of this course, so a lot of the course, you know, this course leverages content that was part of this chipcraft course for the U.S. Department of Defense. You know, it's not literally the same course, but has some commonality. So students in this course, one project was a keypad controller, a timer circuit, SPI controller. Okay, so these two were, actually these last 3 really impressed me. So these were students that had some experience with hardware before. So the one team actually implemented their CPU with a SPI controller to, you know, stream data to the CPU to be able to program the instruction memory through a host computer. And then similar for the UART project. So both of these projects were sort of at the stage where they showed signs of life, showed that the data could be streamed, not necessarily robust, but you know, showing basic operation. And and then this last one was exploring a flow called OpenFPGA, which is for constructing FPGA circuits. Actually designing the FPGA versus using the FPGA. So this student used that flow targeted to tiny tape out to build one of the basic building blocks of an FPGA on the FPGA. So he designed an FPGA for the FPGA, well, then for the ASIC. So again, these three projects are all beyond what I would expect you to do and beyond what I would encourage you to define as your project. But, just to put that out there and show that these sorts of things are possible. We had a three-person team, so this is the second iteration. We had a three-person team doing a calculator-based project. Another project that was like off the charts. We had a team of 3 students that had some experience with the AES encryption algorithm in software, not in hardware. They were new to hardware, and after learning hardware, they thought, wouldn't it be cool to implement this algorithm in hardware? And they did that, and I thought it was amazing. We had a team of 2 doing a traffic light controller, a die roller, 2 individuals separately doing a die roller project, a multiplier circuit, a stopwatch. One team implemented a UART connected SHA hashing algorithm, another amazing project. Unfortunately, it was too large to fit, so they didn't tape it out, but they did design it and it was functioning. And then a team of 3 did a timer game. Okay, so hopefully those give you some ideas. I think we'll take a break and brainstorm a little bit. There are also various things, various features of TL Verilog that we haven't talked about that weren't necessary for our calculator, for our CPU, that may be useful for your projects. So I think after we have some time to brainstorm, I'll come back up and just do some live demo of other aspects of TL Verilog that might be valuable. And I'll wait to do that until we have a sense of what the projects are, because depending what the projects are, different things might be useful. But anyway, those things are, many of the projects that you do, the trick with hardware is that it runs fast. So when you're trying to do something that you can physically interact with and play with, you may need to slow down your hardware to the point where you can see what it's doing. So I'll just sort of walk through some suggestions for how to design circuits that are running slowly. TL Verilog has constructs for hierarchy that we didn't need for the CPU. So this is replicating logic. Anytime you have anything that's replicated, it's useful to know. And you may be doing projects that are leveraging Verilog IP. So how do you code up TL Verilog logic that uses Verilog IP, Verilog modules, macros, functions? Or how do you code, if you're doing a project that's pure Verilog, how do you do a pure Verilog project in MakerChip? You don't have to use MakerChip. You can work outside of MakerChip and just do a pure Verilog project and use the tiny tape out repository that's built for Verilog projects. Okay, so let's brainstorm a bit and see what you can come up with. I know one of the groups was already planning to do a 8-bit CPU project, but I'll just go around and help you guys brainstorm. We also may have folks online that are also putting project ideas together. Dr. Bopu, they've got an ability to communicate, right? The folks that are online, so feel free to shoot some project ideas out to us, and we'll try to give you some feedback on those. Yeah, so there's another option here I forgot to mention. So this was created more recently by folks that are associated with the Tiny Tapeout group. So this environment is called VGA Playground. It's built specifically for Tiny Tapeout projects that want to use a VGA controller. So it gives you kind of the shell for VGA support, and it gives you the environment that shows you in simulation what your project's behavior is. So this is, whatever VGA project, and this is its VGA output. So it's got a bunch of examples here, right? So this project is displaying stripes, different displays. So the Tiny Tapeout folks used this platform and ran a contest a couple months back, maybe a year back, I don't know, to create, visual displays, right? The winning entry was quite phenomenal, actually. But this is an option, right? Basically, in this platform, you're coding your Verilog logic and seeing what that logic does. So it's similar in some respects to MakerChip. There's no native support in here for TL Verilog. If you did want to do a TL Verilog VGA display project, you could work in MakerChip to create your TL Verilog and drop the Verilog in here. But so in this platform, right, as opposed to MakerChip, in MakerChip you kick off the simulation, it collects the entire wave data and displays that to you in sort of batch mode. In this environment, it's continuously running. Okay, so they got a bunch of sample projects. But this can be fun to play around into. You can do something more graphical and hook up to an external device that's a little more interesting than a couple blinking lights. Yeah, this fits in a tile. I don't know the actual area that's consumed by the VGA controller itself, but I think it's fairly minimal. So I don't have data points, but I believe you can do something, I think you still have most of the tile available for your project, so whatever you can do in a tile. Yeah.
Is there any way that two tiles can communicate with each other?
Not, I mean, not on chip. Actually, one of the projects that was done in the last workshop I did, the students set up logic that could talk between two boards. So they played with two of these FPGA boards and hooked up a little communication path between them and just passed some data around. But yeah, there's no direct communication channel between two projects inside the chip. Yeah.
Like, let's say 4 projects, let's say you have only one chip, right? You have to select one tile per chip. Like in chip, we have each tile per project, right? I mean, it will be a single chip, we need to select between 4 projects.
Yeah, you select one project at a time. So you'll have access to all 4 projects if they all go out on the same tape out, but one at a time.
Tiles can communicate with each other, then you can have one tile for VGA, one tile for CPU, and it can be a whole processor. And so if tiles can communicate with each other.
Yeah, it's a good thought. I don't believe there's any ability to have tiles talk to each other. So a couple things actually, now that we have some sense of what's happening with projects, you're still working on defining them, but since I'm going to be leaving at 1 o'clock, it might be good to go over some other aspects of TL Verilog that might be useful to you, how you integrate with Verilog. Some of you are looking at projects that leverage Verilog. So let me just take a little time to jump into Makerchip and, I don't know, demo a few things. So let's see. The things, well, let me start with hierarchy. Your project might benefit from this. I'm not thinking of any others specifically, but um, so yeah, maybe I'll just code. Um, so hierarchy is used to replicate constructs, right? So your project, for example, is using a stream of data and operating over that stream of data. So as the data shifts in, you have n copies of that data, right? You're currently hard coding, this is my data one, this is my data two, my data three. Later, you're going to want to extend that. Instead of doing 3 pieces of data, let's do 5 pieces of data. So how do you support that? How do you avoid just all the cut and paste associated with each piece of data? So you can replicate however many you want, right? You're starting with 3, so let's create 3 pieces of data. So this just gives you context for 3 replicas of something called data. That's all it does. And if you want to assign, the value, maybe it's how wide's your data, 8 bits. We'll go with a byte. You can make an assignment for that data. In this case, data 0 is going to come from outside. So let's say we have a signal also called value, but in different contexts, it's a different thing. Equal to, I'll just assign it to something arbitrary at this point. Hexadecimal 55. So this expression for value is going to hold for every one of these 3 values. I want data 0 to be a little bit unique. So if we're talking about data 0, we want to assign value to this value. So the syntax here, pound data is my data index, right? So I've got 3 copies of data, 0, 1, 2. Pound data is a reference to that value, 0, 1, or 2. So if we are data 0, then hook up this value to this value. So the top level context is implicitly top. This is a reference up to the top. So, and down into this value. If we're not data 0, then we want to assign the value each cycle to the previous value. So the previous data's previous value, right? So we reference value, right? That's this guy, but we want the previous one. So we can do data minus 1, value, right? So we're referencing up the hierarchy to data indexed as my index minus 1. So for data entry 1, this is going to be data entry 0. Its value, we want the previous one. So it's shifting cycle by cycle. So we can do it that way. Also, I don't know the nature of this. Is this shifting every cycle? Yeah, so the other way to do it is just to put it in a pipeline. Shifting one every cycle is the default behavior of every signal in TL Verilog, right? So you might do that as well. We've sort of manually constructed the natural behavior of TL Verilog to shift data. Let me also open up some other examples of hierarchy. So this is a using hierarchy for the Pythagoras' theorem example, right? So Pythagoras' theorem has two inputs that both get squared, okay? Leg 1 and leg 2. Why are we calling them AA and BB? Why not call them 1 and 2? So we'll call them coordinates 1 down to 0, and they each get squared. We don't have to cut and paste that expression. And then to reference the squared values, you would reach through the hierarchy, right? Into coordinate 0 square, into coordinate 1 square. Okay, so it's a bit, syntactically, it's a bit lighter weight than for loops and declaring arrays, stuff that you would do in Verilog. If we wanted to do a 3D distance calculation instead of a 2D distance calculation, now that we're parameterized, you could just change the parameter value. We do have to add in the third coordinate here. And there's actually a way to code this line so that it's parameterized as well, but we'll just leave it this way. So now we've got a 3D distance computation instead of 2D. So you can use the replication for tiny things like the examples I showed. You can use it for larger things. You use the same construct to replicate CPU cores in a multi-core design, right? So the CPU that you built, if you want to build a multi-core, just indent everything and put /core, 9 to 0, and you've got yourself 10 cores. And then you can add the logic that will hook them up. Just as another example, so this simulation is something called Conway's Game of Life. I'm sure many of you heard of it, probably not everybody. But it's just a simple set of rules for each cell based on whether the neighbors are alive or dead the cycle before. So for this, we create a hierarchy. We create the y dimension and the x dimension. I thought there was visualization with this. So just a slightly different version of the same code. This one's parameterized, so I'll look at the navTLV. Right, so we've got the y dimension and the x dimension, and then within each cell, we've got the logic that's computing whether that cell is alive or dead each cycle. So this is counting up rows. This is counting up, summing up the counts of rows. It's basically doing a 3x3 matrix of the alive values and summing up how many are alive in that matrix for each cell, and then based on that, computing alive. And we also have visualization for that. So this JavaScript code is defining the representation of a cell, and the visualization infrastructure replicates that out to create the grid, and you can simulate. Okay, so basically, you can use this construct to replicate logic, to reference through the hierarchy, the references like this. So this is summing my left neighbor and my right neighbor. So this particular reference is to my left neighbor. So the reference through the hierarchy needs to start with either a child in that hierarchy or an ancestor in your hierarchy. Here, this reference is referencing into my neighbor in the x dimension, so it's starting with the x hierarchy and referencing the -1 um, index. The goofiness here with this expression with modulo is actually just making sure that we're not referencing off the edge of the matrix. So we do -1, and then we use +10 to stay positive, and we modulo that with 10. So it's going to be my left neighbor with wraparound. But in any case, this is just an expression that references my left neighbor. Right here, there should be a pound, but this actually works without it. But you saw before I was using pound or hashtag, whatever you like to call it, as a reference to my index, right? So XX here should have that pound, and that's a reference to my own index, -1, and just using the +10 so the modulo stays positive and does the correct wrap. So I'm referencing my left neighbor, I'm referencing his previous alive value. You can also reference through pipeline. You know, a pipeline is part of the design hierarchy. So if I needed to reference through the pipeline here, I can reference, I can do a reference that starts with that. I can then do YY. If I don't specify a range, that's going to use the YY of this current context, myself, basically. So I can just do it this way. So this part that I just added does nothing. I'm just starting my reference higher up in the hierarchy and drilling down. Okay, so you can, create more complex designs that have replicated logic, and that replicated logic can refer to other replicas and other logic elsewhere in the hierarchy, etc. So that's hierarchy. The other thing that's worth talking through is integration with Verilog. So, let's see what examples I have. So this one is just a simple example of the code structure that you can use in MakerChip to set your project up so it properly has kind of top level functionality. That your top module is your test bench, and then the test bench instantiates a design under test. We just sort of dropped everything into the top level, but you should generally have a test bench that's controlling your logic, and your logic should be placed into a module. So here the module is computing Fibonacci series, right? So here is our separate Fibonacci series module that has a module interface that's appropriate to Fibonacci series. You need clock and reset. We've got an input run that starts off the series, and it outputs the value. Okay, so this, in this case, is our module under test that starts with module, ends with end module, and has TL Verilog code defining its guts. Right, so we're just hooking up reset, we're hooking up run to the Verilog interface signals, and we're doing our Fibonacci expression and hooking up the output value. Right, so, this is hooking up TL Verilog logic to Verilog logic in the sense that it's connecting Verilog to Verilog signals and defining module. Everything here in the top level module that talks to the MakerChip platform, this is all Verilog code for the test bench. If you want to instantiate Verilog modules, Verilog macros, Verilog functions within your TL Verilog context. That's perfectly fine. You can do that. The cleanest way to do that is to explicitly use an SV plus block. This creates an expression that uses system Verilog syntax, but you can, within that syntax, reference TL Verilog signals. So if I had a module called foo, I guess, yeah, and I wanted to instantiate that in an instance also called foo, and it has parameters such as reset, we'll pass run, right? We can use the TL Verilog pipe signals as signals for that module instantiation. I think that needs a semicolon. Forget. So, yeah. So basically, if you're leveraging existing IP that's in Verilog, you know, you find a SPI controller that's written in Verilog, and you need to instantiate that. You want to use TL Verilog for the rest of your surrounding logic. Yeah, you just instantiate. I'll call this SPI. Right, so I can instantiate my SPI controller that way. Here I've done this top level without an explicit pipeline, but as I've said before, I like everything to explicitly have a pipeline. You can do this in context. So you can have a SV plus expression block participating in your pipeline. If this module is purely combinational, things are pretty straightforward. If this is sequential, right, maybe this is a memory. The memory might have, you know, we're going to have a write data input, and we're going to have a read data output. To fit this naturally in the pipeline, the way that we did in the workshop, the read data is going to be associated with a pipeline stage. The write data is going to be going to be associated with a pipeline stage. This whole expression, all of these references are associated with pipe at 2. So if, for example, the control signals for a read, maybe it's better to look at read enable, right? So if the read enable is a stage 2 signal in our pipeline, the read data associated with that probably comes out of our memory a cycle later. So the natural flow of that read operation, the data is in the next pipeline stage. Since this whole module instantiation is in stage 2 of the pipeline, this read data coming out, you know, to name it, time it appropriately in our design is really a stage 3 signal. So when you hook it up, you can use an ahead by 1 to properly associate this with stage 3. Okay. Now, even though this memory was not written with TL Verilog in mind, it's not written in a timing abstract way, still using this syntax and using the relative references, this whole expression is timing abstract. We can move this to stage 3 and retime our pipeline. That's all good. Okay. One other thing about this that I've ignored so far is this is not quite correct. So Sandpiper needs to understand for every expression what are the input signals, what are the output signals. Normally for expressions like this, it's parsing the expression syntax, it's looking for the equals, and the left-hand side and the right-hand side are distinct. When you're calling a module, instantiating a module, there's no inherent knowledge from the syntax of what's an input and what's an output. So when you're in SV plus syntax, Sandpiper is not interpreting your expression at all. it's looking, well, it's interpreting enough to pick out the signal references, but it needs to know what's an input and what's an output. So the signals that are assigned, which in this case would be the read data, need a double $sign to say this is an output. And of course, all of these references you can reference through the pipeline. So if I need to grab my Fibonacci value, for example, as an input, you can reference up the pipeline. I'm referencing from stage 3 to a signal that's by default in stage 0, so I can reference that. Yeah, the double dollar is explicitly identifying the signals that are produced by the expression. Right, so the TL Verilog processing of your design needs to understand what signals are inputs and what signals are outputs of every expression. And since there's nothing syntactic about this expression syntax that makes that clear, we need to be explicit in the syntax that this is an output signal. Hmm? I didn't have it elsewhere in the code. I'm just doing this example in memory, but read data would be the data coming out of the memory, so it's an output. Yeah, so if you have a clock input to memory, for example, which you should, you can reference this system Verilog clock. This one here. So here I'm just showing an example reference to this val signal. So this is, first reaching up to the top level scope, and then I want to reach into the proper stage. I'm doing this expression from stage 3 of my pipeline, and I'm reaching across from this pipeline to the default pipeline. So if we do this, this would be a reference to the default pipeline stage 3. And so that would imply flip-flops on val. Val is defaults to stage 0, yeah. No, this is, if you do this, you're in stage 3 because your expression is in stage 3. Right. And actually, if I were to compile this, there would be a complaint. When you're reaching from one pipeline to another pipeline, you need to be explicit. So, just so you don't forget. I don't know if this will compile, but maybe the diagram will help if it does. This is legal, and also this is legal. Yeah, it's just a special case for 0, which we call natural alignment. So this is looking ahead in the pipeline by 0, behind in the pipeline by 0, right where I am by 0, all the same. Anything else about integrating with system Verilog? Yeah. Yeah, let me just do, well, what are my errors here? So I don't have mem, that's going to cause an error. Oh, actually I do have a diagram there, don't I? Okay, so the Verilog code is not legal because I don't have a definition for mem, but we can still get the diagram out of this. So looking at this, I guess this is what I compiled with ahead by 0, right? So this is a reference to stage 3. So val, which is here, needs to get staged out to stage 3 to get connected to my expression. So this box here is my expression that for the memory that's producing read data. So it's taking a read enable, a reset, a write data, right? And it's all in pipe stage 3. And it's taking val as an input that needs to get staged along. So if I change this to look behind by 3, or this is a cross pipeline reference, so I would use the terms ahead and behind if you're in the same pipeline, looking ahead, behind in your pipeline. If you're referencing across pipelines, I would call this pipeline alignment. So I would read this as an alignment of 3. So you're aligning this, the use of this signal to what's in the other pipeline shifted by 3. So I'd call that alignment. So if I do the, align by -3, basically, that's referencing this guy in the same cycle it's assigned 0. Right? So we're getting a direct hookup of val. These flops, of course, we have because val was our Fibonacci series computation. So this is the Fibonacci series loop. And of course, if we go the other way, we create 3 more stages, right? Right, so you can just do the math on the reference. I'm at stage 3, I'm referencing ahead by 3, that's stage 6, so that's a reference to the val at stage 6. And I was doing hierarchy before, let's create some hierarchy. So let's say we're in a hierarchy called higher, 2 elements. So this is 2 copies of my entire pipeline, both doing the same thing, both referencing this top val signal. So yeah, the only last thing I wanted to say is within MakerChip, if you want to include external content, an external Verilog include file, you basically just do a tick include essentially of that Verilog by URL. You can also tick include TL Verilog library content, which we do in our CPU template. Of an array. You'd use hierarchy. Yeah, so right. Right, and the benefit of that is when you're referencing into that hierarchy, if I had a reference from outside, right, if you have an array reference, there's nothing explicit about that reference that says what the indices are that you're referencing. But here, if I'm referencing through the hierarchy to, to go through the whole hierarchy to reference what do I call it? Read data, right? Of course, that's not a valid expression because it's 32 bits, but your reference this way, instead of sort of being just read data sub 0, the sub 0 has a name, it's higher. It makes the references more meaningful. And it's also more general, right? An array replicates a single signal. And if you have other signals that also need that same replication, you replicate them. Here you just give yourself replicated context. cleaner. It's all doing the same thing, but once you get comfortable with this, it's a bit cleaner. So yeah, we can go over the syntax when you need it, but you can include external content by URL, whether it's Verilog context, the content, or TL Verilog content. MakerChip only supports single file editing, so if you're working with multiple modules or something and you're editing both of them, stick them all in the same file, work in MakerChip. When one of those modules stabilizes, you might want to put it in a library and check it into GitHub and reference it through its URL. I think that's everything you need to be aware of. We can, as you're using this stuff, I can help you with the detailed syntax.